Hello everyone, my name is Dipesh Chaudhary and today we are going to take a deep dive into one of the most important concepts in statistical inference and hypothesis testing, the F distribution. And here we go. Here are some few agendas and overview we will cover today. First is an introduction to the F distribution. Second is the mathematical formulation and the key mechanism. Third is the graphical representation to visualize the F distribution. Fourth is an overview of ANOVA and its application. Fifth is a step by step F test example. Sixth is a common pitfalls and best practices. Seventh is historical content and advanced consideration. And eight, finally, a summary and key takeaways. Now let's talk what's F distribution. The F distribution is a continuous distribution used to compare variances. It was developed by Sir Ronald Fisher and serves as the foundation for statistical tests like ANOVA and regression. For example, imagine testing whether different teaching methods affect student performance. Researchers often deal with multiple groups of data, and F distribution helps to determine whether the difference in variance between these groups are statistically significant. Now let's dive into the mathematical foundation of the F distribution. The F static is defined as F equals to U1 slash D1 by U2 slash D2, where U1 and U2 are independent chi-square distributed random variables. D1 and D2 are their respective degrees of freedom. This formula shows that F static is the ratio of two scale chi-square distributions. The shape of F distribution depends on these degrees of freedom. Now let's take a look at some few key properties of the F distribution. First is the distribution is positively skewed and only takes positive values, that is F is greater than 0. It is determined by two degrees of freedom, D1 for the numerator and D2 for the denominator. It is right skewed distribution, meaning it has a long tail to the right. These characteristics influence how we intercept statistical results, especially when sample sizes vary. A large F value suggests that the between groups variance is significantly greater within group variance, implying group means are not all equal. This forms the basis for tests like ANOVA, where we compare several groups means simultaneously. Now let's take a look at the probability density function of the F distribution. The formula is given below, where B is a beta function. Well, breaking it down, we can see that D1 and D2 are the degree of freedom, where D1 corresponds to the numerator degree of freedom and D2 corresponds with the denominator degree of freedom. In the numerator terms, these terms arise from the transformation of two independent chi-square distributed variables. And the term x, we can see in the formula the presence of x in the denominator ensures correct scaling when transforming from a ratio of g-squared variables to a f-statics. The role of beta function in here is we can see that this acts as a normalizing constant, ensuring that the total area under the PDF curve equals 1 as required for any probability distributions. Here are some examples to analyze the graphical representation of the F distribution with different degrees of freedom. There are two key cases. First is low degree of freedom and second is high degree of freedom. In low degree of freedom, the first distribution is highly skewed to the right. It has a long tail, meaning the F values are possible but occurs less frequently. Most of the areas under the curve is concentrated near zero, which shows that small f values are more common. In the high degree of freedom, the distribution becomes more symmetric. As the degrees of freedom increases, the F distribution starts to resemble a normal distribution. It is less skewed meaning extreme F values are likely. This visualizations helps us to determine the F distribution behaves in different statistical tests. When performing a F test, the degrees of freedom play a crucial role in shaping the distribution and determining the critical. Now let's talk what's ANOVA. ANOVA or analysis of variance is a statistical method used to compare the means of three or more groups using F distribution. It determines whether the difference observed among groups mean are real or simply due to the change by using the F-static, the ratio of variance between groups to the variance within groups. The higher F value indicates at least one group differs significantly, making ANOVA a powerful tool for evaluating effects in research studies. One of the most example is in agriculture studies, such as testing different fertilizers to see which one results in the highest crop yield. There are different types of ANOVA tests, but we are going to use one way ANOVA for this test. Purpose is to determine the difference exists between three or more groups. First is the hypothesis. In hypothesis, we have a null where all groups means are equal, and second is the alternative, at least one group's mean is second different. Is calculate sum of squares. There is total SS, that is variability of all data points across the grand mean. Another one is between group SS, that is variability of group means. Another is within group SS, that is variability within each group. And to take out the total SS, we have to add the between group SS and within group SS. Now the third is degree of freedom, where we can see total DF equal is total data points minus 1, whereas between group DF is number of groups minus 1, and within groups DF means total data points minus number of groups. And to check out the total DF, we have to add both between groups DF and within groups Fourth DF. Is mean squares, where between square ms, that is between groups sum of squares by between groups degree of freedom, and within group ms, that is within groups sum of squares by within groups degree of freedom. The fifth one is f statistics. So f equals to between groups mean square by within groups mean square. And the sixth is decision making, where we can see that if the p value is less than significance level, like example 0.05, we reject the HO that indicates a significance difference. But if the p-value is greater or equals to, then we fail to reject the HO that indicates no difference. In conclusion, if we reject the HO, at least one group is different from others. But if we fail to reject the HO, then there is no significant difference in Here any are group. Some common mistakes to avoid when performing an F test. First is ignoring normality assumption. The test assumes that the data within groups are normally distributed. Second is miscalculating degree of freedom. Incorrect value leads to wrong critical F values and incorrect conclusions. Misinterpreting a significant F. A significant result only tells us at least one group differs but does not specify which one group. Now for the best practices. First is verify normality. Before conducting an F test, check the normality whether each group using histograms, QQ plots or normality tests. Transform data if necessary or consider non-parametric alternatives. Second is double check degree of freedom. Meticulously calculate DF and DF between equals to k minus 1, where k is group number of groups, and DF within, that is n minus k, where n is total number of observations. Error here directly impacts the value of the tests. Third is perform post hoc test. If the F test is significant, always follow up with the post hoc test to determine which groups means are significantly different from each other. Historical impact. The F distribution was introduced by Ronald Fisher in the 20th century, and the F distribution has played a vital role in shaping the modern statistics. Its application transformed the experimental design and hypothesis testing, leaving a lasting impact on the research methodologies. Here are some advanced considerations that are focused at when they should be considered. As first is the robust alternatives when assumptions like normality fail, to consider using robust method such as Williams ANOVA or non-parametric tests. Second is multi-variable extensions. The F-test framework extends to MANOVA for cases with multiple dependent variables. Third is Bayesian approaches. Bayesian method incorporates prior knowledge to refine variance analysis. These strategies helps to ensure your statistical conclusions remains reliable even when conditions aren't ideal. At last, here are some key takeaways that are summarized points of the presentation. The first is propose. The F presentation is essential for comparing variance in tests like ANOVA. Second is key property. It always positive. Right skewed and defined by 2 degree of freedom. Third is interpretation. A higher F value indicates significant difference between groups. Fourth is assumption. Always checks normality and equal variances to ensure valid results. Fifth is advanced methods. Robust alternatives and extensions like MANOVA, Bison's approaches can be used when assumptions are violated. So at last, I want to say mastering these concepts equips you to confidently analyze the data and make informed decisions. Last but not least, thank you for joining me on this exploration of this F distribution. Hope you like this presentation, informative and valuable. I encourage you to explore this fantastic world of statistics. The more you learn, the better you will be to make sense of data and drawing meaningful conclusions. If you like to learn more better, here are some differences. At last, the presentation ends. Thank you everyone for listening to me. And if you have any questions, please comment down below.